Hey guys, welcome back to the channel and thanks for watching. You're welcome to Precast Concrete Lifting Course, lecture 6 of 6, which is the final lecture in our lifting course. So this lecture will be all about spreadsheets, the development of spreadsheets, what you need to do to be able to build a spreadsheet to design bespoke lifting for precast concrete. So hopefully when all of this is done, you'll have the tools necessary to be able to design elements such as these large 40-ton, 20-metre long raker beams that we designed and Banner manufactured for Shamrock Rovers. You'll also be able to design roof beams, 25-ton, 20-metre long roof beams. So large, bespoke lumps of precast concrete. They need a little bit of thought to be able to demould and site lift these safely to the codes. Okay, again, thanks for watching. Going to pop you over to Matt. He'll run through the spreadsheet. And again, any questions, please feel free to reach out. And don't forget to like and subscribe.
Okay. So we've covered quite a bit up to now. Lifting, how to calculate the lifting demands, the lifting capacities, tension capacity, shear capacities, the different types of lifters. Some worked examples, lifting with rebar and strand. And now, I suppose, in order to be able to use this kind of information going forward, the best thing to do is to develop a kind of a spreadsheet that will take various inputs and geometry, etc., and give you a design. So this module is focused on showing you how to, I suppose, develop a spreadsheet. Not going into the functions of Excel itself, but just kind of key things that need to be kind of noted. So that's where we'll start. Just okay. So yeah, so this is our standard slide that we had every week, so there's no need to go into that in any more detail. There'll be time for questions at the ends, and the slides will be emailed out afterwards. The last lecture on spreadsheet preparation, all the previous ones have been emailed out to you, so you still have all the slides available. And my email is on the previous slide if you have any technical questions that you want answered. So this module will have a quick recap, I suppose, of the last one, which was the unworked examples, and then we'll get straight into spreadsheet preparation. Last week, we did a detailed worked example from start to finish for a particular unit. It was a wall panel with openings in it. It had to be demolded on the flat, tilted up and on site and installed vertically. So we had a number of different iterations to go through. First time we went through it, the lifters didn't work. We had to think about what we could change. And as I said, there are a number of different parameters, the number of lifters, whether we're going to use a spreader beam, can you afford to leave the unit in the mold longer to get a higher concrete strength, the positioning, additional rebar can get added in. So there's a number of items like that can be addressed, and we kind of showed that down through all the different failure modes and generated kind of summary tables highlighting what the critical factors were. So that was kind of encapsulated. I think it was quite a good example. It took a bit of time to get through it, but when, for example, if you were to do that on a repeated basis, the value of a spreadsheet becomes apparent, so that you don't have to retype out all your formulas again, etc. But I suppose the one caveat is, you must understand what the formulas do and what the inputs and outputs are, and not just taking them with blind faith. So with any spreadsheet, it needs to be used by an experienced person, engineer. So the key parameters, I suppose, excuse me, of a spreadsheet, and I would have said this at the start, is always start with a diagram. A nice clean diagram with the geometry, the position of the lifters, etc. So that's kind of what we've shown here. And that's kind of the first thing that should appear on the spreadsheet on the first page of your report is the diagram. Straight away, a person reviewing it will know what unit it is, will be able to verify what parameters are required. And then beneath that, then as best as possible, try and bring together all your inputs in one location. So we can see here on the diagram, just give me a pointer up here. There we go. We can see here in diagram, so your geometry, your length, your width, your height. So this is a spreadsheet for a typical flat slab. We've got the edge distances, everything is assumed symmetrical, and we've got some other parameters here, which I'll go through a little bit later. We're just trying to identify all the different possibilities. We calculate the weight of the unit, volume by weight, all our different partial factors for lifting and handling, your partial factor on the permanent loads, your partial factor for concrete and steel. So again, they're all in as manual inputs. And then it's convenient to set up your spreadsheet, bring your two sets of calculations, one for your in factory and one for your on site, bringing them through the calculation together, so that you're only calculating them in the same location. And it makes it easy for reviewing and, I suppose, understanding where adjustments can be made to improve your design. So you can see here what we've done is we've one column for the in factory calculations and we've one for on site. The numbers used here are the same in this particular case, but principally the idea is to bring them all through at the same time. One thing I suppose to bear in mind is try not to, when you're developing a spreadsheet, try not to develop it to cover every single possible scenario, because it gets overly complex that way. But you can understand a lot by simplifying things and letting by building in, for example, override boxes to allow you to still use a relatively straightforward spreadsheet for more complex scenarios. So we have an override box put in here for the weight of the unit. And say, for example, this was a flat slab, but it had like a nib going around the outside or an upstand or something like that. All those would add to the weight of the unit, but not necessarily affect the design of the lifters in terms of the geometry, etc. So once you have the basic geometry, and if there was slants or slopes, etc., you can input the actual weight of the unit that you get from your model. Similar to that is the mold area, is that if you have, again, nibs or steps in the soffit of your unit in the mold, you can account for that by adjusting the mold area. That's kind of all your inputs on one clean page. Like we would have done the calculations throughout the lectures, it's good to set up your spreadsheet like that, in that logical flow. And the first step is to calculate the applied load on the anchors. So way back in lecture 1 is where we covered all that information, and it condensed down into a couple of lines in your spreadsheet. And it's what you're looking for is your 3 parameters with a bit of trigonometry in there. So the tension load in the chain, the tension load on the anchor, and the shear load on the anchor, which is due to the chain angle. And again, we're bringing through the in-factory and the on-site values at the same time. And we've put in an override box there, for example, because, again, things might slightly change and you just want to have that ability from a hand calculation or something like that to basically adjust the parameters to allow you to do that. Next step would be something like selecting the suitable anchor. So once you have the applied loads, you can then select an anchor from the brochure from that, whether it be a wavy tail socket or a lifting pin, etc. And then understand as well the parameters that you need from that. So the anchor size, the anchor length, etc. And building in little checks along your way, just to show that in this particular case, we had a tension load of 1.7 tons in the chain, and we ended up using a 2.5 ton anchor. So a little check saying, is 2.5 greater than 1.7? The answer is yes. And then a little green box to signify that. So kind of a visual indicator to state that all is going good so far. Then I suppose it's always good to have references to where you're getting all the information. So where there's particular inputs required, like all these K factors that we would have discussed throughout the capacity lectures 2 and 3, having a reference there for, again, someone picking up this that's not entirely familiar with it or that needs to check it and they want to understand where the values can come from. Having those references in there are very valuable. Another thing I would add, and I suppose not shown on this particular set of slides, is where possible to add in the actual formulas onto your spreadsheet as well. So someone actually, if this is a printed out report, they don't have the spreadsheet, the Excel file that it was built from, so they can't dip into the cells and see what formulas were used. So having the formulas there present on the sheet is very helpful for understanding, I suppose, from a checking point of view, but also from a I suppose a design point of view. When you come to a stage where the design doesn't work, and you can just read back through the list here of the formulas that are being used, and you can see the parameters that are used, and then therefore you can see what parameters can be improved. You know, your concrete strength, your edge distance. You can see what can be done there to make it work. So what we've set up here then is the concrete cone. All the tension checks first. So we walk down through it again, half a page per check, nearly even less, and you can kind of condense it down to allow you to calculate the capacities, bringing through again your in-factory and your on-site values at the same time for concrete cone, for the maximum pull-out capacity, concrete blowout and splitting failure, etc. So, I mean, a nice flow to the document. So we're down at this stage now. You've calculated the loads in the anchor, you've selected an anchor, and then you've taken that through all the tension checks. You could add in, if you wanted, more visual checks at each step along the way, or you can save it all for the summary table at the end. Either way is good, but the summary table is probably the most valuable because you can see it all on 1/2 page, what is happening. Then the next step would be to check all your shear failure modes, if they're valid or not. And again, I suppose highlighting, you can see there's a trend on this set of slides that all manual inputs are in orange, and all kind of calculations are in a white box. So having that distinction kind of will, I suppose it's twofold. It'll be clear what is required to be input manually, and what is not, but also from a quality control point of view, that, you know, the formulas that are in behind these cells, behind these numbers, don't get, I suppose, changed accidentally and saved over for the next user then that could potentially not recognize that and be working with an invalid spreadsheet. Again, little diagrams partway through your spreadsheet is also good, because it's dealing with a specific check, and this particular one on edge distance, you know, it's very good to have those dimensions beside where they're being used in the formulas, so it can be clear, kind of, rather than having to flick over and back through too many pages to basically see what the parameters are. And this slide then finishes out the shear checks. So you got your step 4B, local concrete crushing, and step 4C. The two of them shouldn't read local concrete crushing, this should read pry out. I'll get that amended before we issue out the slides. And then the final step then, step 5, is to summarize all the results. So in a nice, clear half page, you can see all the steps, all the checks that they came from, the capacities that were calculated, the demand that was brought forward from step 1, and that's cross-checked against the capacities to get your utilizations. Again, nice visual approach here, all green lights. If any of those were red, we therefore have to address it and go back through the spreadsheet and I suppose determine what's the best way to address that non-compliant particular check. Interaction checks, again, they're also important and mainly govern when you have larger angles of chain. And then the final aspect is, okay, what if some of these checks do fail and that any of the previous parameters, such as the concrete strength or number of effective lifters, cannot be changed for whatever preferences you have? Well, then you can then look at supplementary reinforcement. So we spoke about that in lecture 3. Supplementary reinforcement came, I suppose, in 2 forms. One to check the tension failure modes and one to take the shear failure modes. And again, we just have 2 quick slides on that in the spreadsheet. By having these at the end of your spreadsheet, if they're not required, you don't need to include them in your report. So they're easy enough to delete out on a case-by-case basis. So they're not mixed up within the main body because they're not always required. And again, it just keeps it cleaner. If you had them included and you weren't using them, then a checker might query exactly what's the relevance of it. So again, understanding how you build your spreadsheet, what it does for you, quite clear. Nice label diagrams of the dimensions. So if you were to present this to your drafters, then they can clearly see then what the dimensions need to be in terms of the additional reinforcement, the anchorage required, etc. So, and then after a number of iterations, you're all used to how your spreadsheet works, and then you can basically have a more streamlined process. Anchorage checks, and then the last one then is just again the shear checks. What is the distances that are being used, etc. So that's the long and short of I suppose spreadsheet preparation, and it's kind of up to yourselves to develop it in whatever way you would like. But again, to be clear on what the inputs are, the outputs are, what you're trying to achieve. Try not to capture everything in one particular spreadsheet. You can create this multiple times and have it slightly different. So you could have one for slab lifting, you could have one for wall tilting, you could have one for culverts, or because they're different shapes, but they're a general enough shape at the same time. So you could have a couple of multiple different ones developed, rather than trying to have one single spreadsheet that captures every single option. You'll find yourself getting into difficulties trying to allow for all those different options in the formulas that you put in. So it's easier to just create multiple different options. This slide here is then a quick, I suppose, a few tips and hints on spreadsheet automation. So Excel is a powerful tool, and you can do a lot with it in terms of automating. So things like drop-down menus. For example, when you're selecting the lifter, you can have all your lifters pre-built into it in terms of the drop-down menu. And if you're 2.5 ton, your 5 ton, your 7.5 ton lifters, all there in a drop-down menu. Diagrams and labels, again, it's key to have good diagrams. And you can have a screenshot, you can sketch out a diagram and insert it in, or you can develop a dynamic diagram that updates automatically when you change the input parameters. Color-coded checking, another one. As I said, use a traffic light system. Green light means good, red light means bad, and it's very clear then from a glance if your design is working or not. And I suppose the logical flow, like we said, start from top to bottom as you would normally do it. Get all your inputs in there, calculate how much your load is in your anchor, select an anchor, work down through all your checks, tension, and then shear, and then summarize all your results after that. So you can set up your calculation like, rather than spreading it all over your Excel sheet, you can set it up in a kind of a narrow vertical format such that you can print it in a report nice and clean and package it up and issue to the client, etc. I spoke about the clearly identified manual inputs. We have used orange in this particular case. So again, consistency is the key for anyone that in your offices, in your businesses that are going to be developing spreadsheets and such like that. Consistency is key, so that everyone knows, I suppose, what the standard formatting would be. And then the last item there is just the override boxes to mention again. We put them in blue, and this just allows alternatives to be built into the calculation. And as I said, it's especially useful where the development of the spreadsheet for more complex units with nibs and recesses, etc. It's not justified to build a spreadsheet that will basically garner for all those situations. And the last slide here should work is a walkthrough of essentially just what I'm after covering. Let's see now. There we go. Sorry there. Yeah, this was actually it was a pre-recorded, so it was I thought it was playing in the background. So yeah, so basically this is this is just a simple walkthrough. So we'll let it play there. Simple walkthrough, just flowing through it. So previously you saw the lifter, the diagram being set up, input our parameters, and this was a dynamic diagram that we had here, and it builds basically for a particular scenario. This is again nice simple one for a flat slab. It's symmetrical lifters. If you had one for asymmetrical lifters or a different shape, you could use this particular spreadsheet, or you could create another one for it. But it's just all about just highlighting the value of the drop-down menus, put in your lifting and handling factors, your concrete cone factors, etc. Moving on, then you just start populating all your parameters again. It's all this first half page gets the majority of your parameters. Little blue text to kind of notes just saying what is the actual values used to lifting load coefficients, etc., and our angles. So one of the things that try to do is just make it as clear as possible. This is your drop down for your mold. So 1 kPa, assuming an oil steel mold, and that automatically generates. So trying to reduce the amount of manual inputs to the bare minimum. So when we move on to the anchor applied load, it automatically gets calculated based on the weight of the unit, and then we can basically calculate a suitable anchor from that. So and we have our override boxes up there as well. We can put in a different value, and that will basically get carried through. So taking that value, then we can, from another drop down menu, we can take the whether it's a lifting pin or a wavy tail socket, and again, you know, the tables from the brochures, you can bring them into your spreadsheet, digitize them, and make it available here. So if we select a 2.5 anchor, it obviously comes up as not good because we needed 8.7. So 7.5 is still not there. And then, you know, we put in 10 and it all gets a green light there. So the anchor length is the next thing. So we need to make sure that we have the anchor length selected that will actually fit in the unit. So by selecting a larger anchor there, 340, it, you know, flags to us as not okay because we had a thickness of 300 in there, and the selecting, you know, work down through the options available to see what we can actually fit in there. You know, those lifting pins are in set lengths, so we just need to select the correct one. And with the dome head recess on the lifting pin, there's an extra 10 or 15 mil that need to be accounted for there as well. So when we do that, we can go back up to the top and have a look at our concrete cone failure projected area. So knowing the anchor length is 265, and from the formulas that we discussed back in lecture 2, the projected area is 1.5 times the effective depth. So a little calculation here just to say that the 1.5 times will be 397.5 millimeters, and we can just populate all that, and it comes in there automatically as our projected area. So 397.5, it's less than our minimum smallest edges to 400. But if we, for example, if we change that to say 250, you know, errors pop up again. So anything that needs to be checked should have like a traffic light system in place to highlight whether it is working or not. So you can see from the diagram that the concrete cone projected area is outside our unit, which isn't valid. So we need to adjust the concrete cone projected area, which brings that down to 250 because that's our limiting factor there. And you know, that'll mean then that we will have a reduction factor when we calculate our concrete cone. So that's all good. Step 1 done. Step 2 done. And we can move down now to step 3, which is the beginnings of calculating the capacities and the concrete cone capacities. So is the first one we check. You can see there that the ratio is in as 0.81. So that's as a result of our projected area. That's forward on there. We have some factors, so the K factors. Again, they're the only inputs. All your other values here are a formula, and so condensing down from what we would have had in the lectures, you can see that the number of manual inputs now has significantly reduced. So it's really just the K factors. Our concrete strengths are brought in here. So in factory, again, these are all pre-populated with your typical concrete strengths according to the Eurocode, and we can just adjust them quite easily using the drop-down menus. And then that's when our checks start to come to value. We get a final design capacity for our checks. And then we just have statements in place where the results are coming from, what formulas are used. and our reduction factors. So if we go back up here, we can see if you calculate the area of that divided by the critical area, and we change it back to 400 so that we don't have an edge distance issue, you can see that that factor becomes 1. So again, it's just having those kind of formulas all linked together, so that, you know, again, it's the flow and the amount of inputs required. So I'll just put this back here now to 250. The next check, step 3B, the pull-out capacity. There's not a huge amount to be discussing that again. All the formulas, you can see them back in the previous lectures. And again, the K2 factor is required as a manual input. The pinhead diameter and the foothead diameter are, you know, parts of your brochure tables, so you can digitize those tables and bring them in. Blowout then is not required in this case. Again, the reasoning why it's not required, we put in a statement saying, you know, because of the minimum edge distance and the depth of the anchor, the edge distance is not less than half the embedment, and therefore don't need to check load. So those kind of checks, whether you need to flag whether it's needed or not, it is also good for the user. Then concrete splitting failure will be the same. So there's a number of ways. We spoke about the simplest way according to the code, by just ensuring that you have enough reinforcement around the rebar. If, for example, you didn't have reinforcement in there, if it was an unreinforced piece of concrete, you could calculate a splitting failure as well. And that's kind of what the form is here, and it's all in the code here, section 7.2.17 of EN 192-4. So that's kind of like that. So the manual inputs in each of these steps, there's only one manual input required for each of those checks really, and it was either the K factor or the reduced area. So you can come up with ways of automating them as well, but it's always good to have those whole points, I suppose, in your calculation, so you do actually have to think about what you're putting in, as opposed to just blind faith. Concrete edge failure, you know, working down through it again, and having that diagram is quite useful at this stage to understand whether you need to, I suppose, consider it or not, and then whether when you do consider it, is your force parallel or perpendicular to the edge, and that'll signify which angle you put in. So the 3 diagrams here on the right, not sure if you can see them that good, but they're in the lectures where we spoke about that alpha factor, and you know, it can be either 1 or 2 or somewhere in between. So there's a big saving if your shear force is parallel to the edge as opposed to perpendicular to the edge. Moving on down, there's a few more manual inputs to be, I suppose, deciphered when it comes to the shear edge distance. There's a bit more going on in terms of what values are used, but you can try and keep it to a minimum as much as possible. And then again, the actual area, projected area that's required to be used is a function of, again, the edge distance, which was 250. So when we come up here, we have 250 edge distance. So again, you need to ensure that you can achieve 1.5 times that distance, left, right, and down into the panel. So when you work out your calculations, this is the kind of diagram form that we're using. 1.5 times 250 is, you know, 375, and we do have that in this particular case to the left and right, but we don't have it in the thickness. So we have to the left, we have to the right, and in the thickness, our thickness, as we stated there, in the height dimension there is 300. So we just work out that, and we put in a 225 in there, and that'll give us the reduction factor. So that's gone to 0.8 reduction factor for that. So again, it's just logical flow, following through the whole thing. The last 2 steps, local concrete crushing and concrete pry out, there's no, I suppose, critical manual inputs required for that. It can be all automated quite easily using the formula, and then we've just got the summary table then, and it all comes together. You can see if I just click that there. Our interaction checks weren't calculated for some reason. So, being able to identify errors in your spreadsheet, track back why wasn't that calculated, because step 3D, there was something not calculated here. So we obviously missed something back in the spreadsheet that needed to be put in, and it was the projected area, this blank box here for that. So splitting in this particular case was not an issue. So we were able to achieve the full projected area. So all our green light system comes into effect there, and that's kind of shows satisfactory design. You can see the interaction check of 94% in the factory is the governing case. So that's kind of, that would have been the first one to fail if some of the parameters were different. And the last thing really is the spreadsheet, or the section for supplementary reinforcement. So we had a trigger switch there to turn supplementary reinforcement on or off. And again, if you're relying on the supplementary reinforcement, you just start putting in your parameters, what U-bars can you fit in there, etc. How many of them are effective. And we went through how to do that in lecture 3. And the same goes for shear. And with those, you need to make sure that you have full anchorage. So we just have a simple Eurocode 2 anchorage check in there as well. And that kind of will tell you what anchorage you need, so you can do up a final sketch then for your drafters, or give them the dimensions and shape code of the U-bar that needs to go in around the lifter. And I suppose the additional manual input on the shear is the K10 factor, which is the efficiency factor. So it's either 0.5 or 1. So a little drop down box in there for that as well is helpful. And that's kind of it. So apologies for possibly the disrupted flow of this walkthrough. It was pre-recorded, but obviously the voiceover wasn't displaying through for you. It was displaying through on my end, so I had to wing it some bit. So going back up to the summary table, having said that you're relying on supplementary reinforcement means that all the force goes through the supplementary reinforcement. So you could see there from that summary table that it wasn't working, interaction check. So you just need to maybe increase the size of your reinforcement. So instead of B10s, you could use B12s. I don't know, it's kind of weren't quite there yet, but there are a number of factors you can go through to check, all to basically get a satisfactory result. And when you're dealing with reinforcement, supplementary reinforcement, it comes down to the size of the rebar or the concrete strength. In order to do that, there are kind of only 2 ones that you can use. And obviously, if you can reduce the load on the lifter, that'll be a help also. So that's the last slide of the last lecture. And I hope that was somewhat helpful for you to get a feel for what a spreadsheet would look like. So you need to get a good understanding of the formulas, go into it, kind of write them out once in nice clear detail, and populate a spreadsheet based on that. So I'm going to stop there, and if anyone has any questions, please feel free to ask.